All right, Tuesday, March 31st, 2020. Hopefully you guys didn't find the L'Hôpital rule test so difficult. I'm filming this on Sunday night, so I haven't had a chance to see all the tests yet. Anyway, I just wanted to give you guys a sort of an exploratory day to start the next unit. The next unit is going to be called Limit Involving Infinity. So I just want to talk about what is infinity anyway, because everybody brings this up. You know, like any limit involving infinity is going to be infinity of some sort. Well, not necessarily true. But please note that the infinity, this is the infinity symbol, by the way. It's a sideways 8 if you want to trace it. That's how you draw the infinity symbol. You just draw a figure 8 sideways. But please note that infinity itself is not a real number. And whenever I teach calculus and I talk about infinity, I always think about elementary school kids where it's like, infinity. I hate you, infinity. I hate you, infinity plus 1. Well, you know what? The funny thing is, once you take calculus, it's like, there's various levels of. Sorry, we ended up at the same goal of infinity, but you'll see in this lesson. But anyway, think of positive infinity and negative infinity as concepts. The ultimate what if. What if we had the biggest number humanly possible? Or what if we had the smallest number humanly possible? Today I'm going to be focusing on positive infinity, but we'll be working with both positive and negative infinity. And I just want you guys to explore. Just really relax. It's not some sort of meditation video, I assure you. But yes, let's meditate by calculus. That's a fun idea. So let's do some exploring with our x values. So I just want to take a look at something like y equals x, the most basic linear equation. So let me get my pencil and my red pen. Okay. So for instance, this is pretty straightforward. So if I have 1, let's go as x equals 0. Well, y equals x, so when x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 2. You know what? I'm going to jump up. When x is 10, y is 10. When x is 100, y is 100. When x is 1,000, y is also 1,000. I'm just going to jump up. When x is 1,000,000, too many zeros. When x is 1,000,000, y is also 1,000,000. Okay, let me just extend this down a little bit. I didn't think this table was going to get that big. So anyway, let me just map out this graph where this is the x-axis and this is the y-axis. So obviously it's not fully drawn to scale like as accurate. I just want to give you guys an idea. You can agree that this is what y equals x looks like. It's a pretty standard linear equation. When x is 1, y is 1, and so on and so on and so forth. But notice, as x gets closer and closer to positive infinity, y also rises to positive infinity. So as x gets to infinity, y gets to infinity. In other words, when x becomes the biggest number humanly possible off this notebook and on my table, y goes way off this paper to positive infinity as well. So the idea is the limit as x approaches infinity for x is equal to infinity. Not bad. Okay? Yeah, I put it down there. So the limit as x approaches infinity, when x approaches the biggest number humanly possible, y also approaches the biggest number humanly possible. Okay, so let me turn the page. Let's do some other examples. This is more of an exploratory day. So let's take f of x is equal to x squared, right? So once again, just to get an idea, that x squared is in the shape of a parabola. It's a U-shaped figure. Okay. I feel like Bob Ross. Happy little arrows. Okay, but let's just plug in some values of x. So let's just say I start with x equals 1, x equals 2, x equals 3. Let's go to 10, 100, 1,000, a million. Okay, so when x equals 1, excuse the noise, sorry about that. So when x is equal to 1, and we plug it into the equation, 1 squared is equal to 1. Not very exciting, but you see what happens when we get closer and closer to infinity. If I plug this in for x, let me see if I can fit. Nope, I'm going to need a bigger input there. But you can see where this is going, and I haven't even written it. So if I were to make this table, when x equals 1, y equals 1. When x equals 2, y equals 4. When x equals 3, y equals 9. When x, so I would do 4 squared, that'd be 16, 5, and so on and so forth. But if I jump up, let's just say I jump up to 10. 10 squared becomes 100. 100 squared becomes 10,000. 1,000 squared becomes 1 million. And 1 million squared, I'm just going to draw, is it 12? In other words, let's just be honest, that's a really big number. The idea is, as x gets closer and closer and closer to positive infinity, y also gets closer and closer and closer to positive infinity. But even though we both end up in infinity, we're going to explore the difference between x squared going to infinity and x going to, y equals x squared going to infinity and y equals x going to infinity. So in this example, the limit, let me put this down here so it's not so confusing. So the limit as x approaches infinity for x squared is also infinity. So again, just one more, just for the heck of it. 1, 2, 3, 4, 10, 100, 1,000. You know what? You guys get the idea. So I'm just going to stop once I plug these bad boys in. So you can see when I plug these inputs in, I get 1 cubed, which is oddly enough still 1. 2 cubed, which is oddly enough still 8. 3 cubed, which is 27. Okay, now we're cooking. 4 cubed, which is Nintendo 64. I could have done 5 cubed, which is 125. But I just wanted to jump up and show you that these functions don't mess around. 10 cubed is 1,000. 100 cubed, that'd be 6 zeros. Oh, that'd be 1,000,000. And then 1,000 cubed would be 1 billion. And if you're curious about what the graph of x cubed looks like, sort of looks like a snake-looking graph. But you'll notice that the x cubed increases faster than the x squared, which increases faster than the x, and yet the limit as x approaches 1,000,000 for x cubed is still infinity. so just to get a main idea down before I get into the next problem, is that if I have the limit as x approaches infinity for x, the limit as x approaches infinity for x squared, the limit as x approaches infinity for x cubed, the limit as x approaches infinity for x to the fourth, and so on and so forth, that they're all going to equal infinity. And I'm focusing on positive infinity for now. But am I going to give you all these easy problems? No. However, the idea is certain functions reach certain, so I should say, as x gets closer and closer to positive infinity, certain functions make y approach infinity much faster. Okay, just acknowledge that. They're all going to infinity, and yet if you increase the power, the function is more likely to win the race, so to speak. Okay, the last thing I want to go over today is this one. This is where it gets a little bit tricky. The limit as f of x is equal to 1 over x. So this one kind of messes with you a little bit. So once again, I'm going to plug in 1, 2, 3, let me see how much space I have, 4, 10, 100, 1,000, a million. You know what? A billion. Okay. So as I start to plug in, so I've got 1 over 1, which is, well, 1. Let me put that in red so I can. Okay. So now I'm going to plug in x equals 2. So I've got 1/2, which is 0.5. I'm going to plug in 1/3, which is 0.33333333333333, and so on and so forth. 1/4, which is going to be 0.25. And if I continue to make this table, let's say I jump to 10, y equals 1 over 10, or 0.1. Y equals 1 over 100, which is 0.01, or 1/100. 1 over 1,000, keeping with the theme of the red here. So 1 over 1,000, let me get my red, is 1,000th, or 0.001. Now I jump to a million. And if I count on my decimal places, this would be the 0/10, 0/100, 0/1000, 0/10,000, 0/100,000, 1 million. So you guys get the idea. If I plug in a billion here, that it's going to be ridiculously small. So once again, tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths, 10 millionths, 100 millionths, 1 billionths. So check this out. And if you're curious about the graph of y equals 1 over x, we kind of touched upon this in Algebra 2 and PRECALC when we talked about vertical asymptotes. However, we're here to talk about the end behavior. right? And this is not drawn to scale, but in this problem, previously what we've normally cared about is x is not allowed to be 0 because it creates a vertical asymptote. We'll get to that. We'll spend a lot of time on this. But in particular, right now we're just exploring, well, what happens as x gets closer and closer and closer to the largest number humanly possible? Unlike the previous 4 problems, y does not also just jump off the paper upward. It doesn't go to positive infinity. In fact, you'll notice that as x gets bigger and bigger and bigger, y also gets closer and closer and closer to 0. So the main idea, going back to our main idea, if I have the limit as x approaches infinity, if I plug in 1 over infinity, 1 over infinity is so close to 0, it's practically 0. So we say when the limit as x approaches infinity of 1 over x, we say it is 0. Although it will never actually get there. We did that with a billion, right? We did that with, look at all that. 0.00000000001. It's technically not 0, but the thing I like about limits involving infinity, or limits in general with calculus, it's the study of, come on. Come on, man, that's 0. But the idea of, does it actually reach 0? No. But the intent is to get so close to 0, it's practically 0. The same thing over here. If I have 1 over infinity squared, I mean, come on. If we know that 1 over infinity is 0, and we say 1 over infinity squared, that's still 0, or ridiculously, ridiculously small. All right, and we've got 1 over infinity cubed, and so on and so forth. That's still going to be 0. 1 over infinity to the 4th power, it's still 0. So the reason why I'm having today be exploratory is because you need to think what wins the race. So in this one, as x approaches infinity, y approaches 0. So close to 0, it's practically 0. But remember, limits are about intent. Okay? That's all I want to leave you with today. We're going to be doing more limits involving infinity on Thursday. Have a great day.